Imagine you took a hypothetical ideal laser and mounted it on a rotating table. Exactly 1 mile away is a wall in which the laser is aimed at. Now I want you to attempt to conceptualize the amount of precision needed to move that beam 1/100th of an inch over, or about the thickness of a business card, purely by rotating the table from a mile away. This is the level of rotational sensing resolution that the Heidehain RCN 2000 series angle encoder can track at. Now, in the real world of production, where this component would be found, such as within the dynamic environment of semiconductor fabrication machines and 5-axis machining centers, the true system accuracy would increase this analogy closer to 3/4 of an inch. But still, this 2.5 arc-second guarantee equates to a circle sliced into 518,400 slices. To put this into perspective, at a millimeter away, that arc encompasses just 75 to 80 carbon atoms. This is the story of precision rotary motion control. For centuries, simply turning a shaft via brute force was mostly what was needed. Water wheels, steam engines, and early electric motors spun continuously and simply transferred their power through leather belts, line shafts, and mechanical gearboxes. However, as industrial processes became more sophisticated, a new requirement emerged: the need to control exactly how fast a shaft turned, how smoothly it accelerated under loads, and ultimately the microscopic precision of where it transits or stops. By the late 19th century, the vertical growth of cities and the increasing depth of industrial mining operations both hit one of the first limitations of rotation control. Early electric motors were generally single-speed devices that relied on mechanical rheostats, which were effectively banks of resistors that bled off excess electrical energy as raw heat in order to control motor speed. This method was extremely inefficient and produced violent jerky motion. It was entirely unsuitable for passenger elevators or precise industrial positioning. Reversing the direction of the motor also required physical mechanical linkages and electromechanical components that were prone to catastrophic wear, arcing, and failure. In 1891, American electrical engineer Harry Ward Leonard would patent one of the first motor control systems using a counterintuitive approach. Instead of dumping energy going into the main motor, Leonard proposed using a dedicated, separate generator to create a continuously variable power supply on demand. The Ward Leonard drive consists of 3 rotating mechanisms: the prime mover, which was either an AC motor, a steam engine, or an internal combustion engine that ran continuously at a constant speed, driving a coupled DC generator. The output of the DC generator is wired directly to the armature of the primary DC motor that performs the work. Controlling the system occurs within the generator's field windings. Within a DC generator, the field current determines the strength of the magnetic field within the generator, with the output voltage being directly proportional to that field strength. Since a small field current controls the much larger output current, a simple low-power rheostat can be used to regulate it and indirectly the generator's output power. Because the speed of a DC motor is directly proportional to the voltage applied to its armature, this configuration produced perfectly smooth, stepless acceleration across a wide speed range. The Ward Leonard system quickly became the standard for heavy industrial automation. By World War II, the MIT Radiation Laboratory selected the Ward Leonard system for the SCR-584 anti-aircraft radar, where tracking motions had to be smooth and highly responsive to track moving targets. The system possessed an inherent motion control capability that set it apart from other control systems at the time, called FOUR-QUADRANT regenerative operation. In a 4-quadrant drive, the system can handle both the direction the motor turns and the direction of torque in any combination. Torque in the same direction as motion drives the load, while torque against the motion means the motor is braking. In the SCR-584, when the operator needs to slow the antenna quickly to abruptly change tracking direction, the generator's output voltage is dropped below the motor's back EMF, or the voltage the spinning motor produces on its own. As the antenna's rotational momentum drives the motor, it momentarily turns it into a generator that pushes power backward through the system, acting as a smooth, controllable electrical brake. For radar tracking, where the beam had to settle precisely on a fast-moving target, this transition between driving and braking made aiming smooth in both directions. Despite these advantages, the Ward Leonard system had one key limitation. Even with the control commanded to 0, the generator couldn't reliably hold a true stop. Its iron core retained a little residual magnetism, producing a faint phantom voltage that made the motor creep. This required a solution in which the generator's field winding is connected across its own armature, driving a field current that opposes the very magnetism creating it. So the generator cancels its own residual flux and settles the output to a true 0. Beyond robust speed control, the emergence of mechanized naval warfare during the World Wars introduced a need for absolute position control. By World War II, the aiming system of battleship guns was done by calculations made by analog computers. These systems needed a way to transmit the exact angular position of a remote computational shaft and force a secondary mechanical shaft to match it. To solve this, General Electric developed the Celsin around 1925, which was later referred to as the synchro. A synchro effectively functioned as a split electric motor. When the rotor of the transmitter unit was turned, the resulting electromagnetic imbalances would force the receiver unit's rotor to snap to the exact same angle, even across the long runs found in a warship's fire control system. The concept would evolve into the resolver, an analog rotary transformer that is still in use today in extreme environment mechatronics. The resolver has a rotor winding and two stationary stator windings positioned exactly 90 degrees apart. And the AC excitation carrier wave is fed into the rotor winding, inducing a voltage in each of the two stator windings. Because the two windings are physically offset by 90 degrees, their outputs form a pair of amplitude-modulated analog signals, with one tracking the sine of the shaft angle and the other the cosine. By calculating the ratio of these two voltages, the exact absolute position of the motor shaft can be determined at any given moment, even when the shaft is stationary. Because resolvers are purely electromagnetic blocks of copper wire and iron, they can easily survive extreme temperatures, high physical shock, heavy vibration, and even operate in oil, making them a popular choice for aerospace, military guidance systems, and heavy industrial use. Despite their robustness, the analog nature of resolvers quickly became a limitation. This is primarily due to limits on the frequency of the excitation carrier wave, which constrained their signal tracking bandwidth and dynamic accuracy at high shaft speed. Furthermore, as digital control systems emerged, resolvers proved more vulnerable to quantization errors during analog to digital conversion. These limitations created a need for a natively discrete, high-speed method for determining rotational position. In the late 1940s, the Baldwin Piano Company was experimenting with ways to electronically replicate the complex harmonic sounds of European cathedral pipe organs. One experimental approach used spinning glass discs photolithographically etched with varying patterns of opaque and transparent segments. As light passed through these spinning optical tone wheels and struck early photodetectors, the alternating light and dark pattern was translated into electrical waveforms corresponding to complex musical tones. In 1951, the U.S. Army Signal Corps recognized that the same concept could be adapted to slicing light into exact rotational angles for pointing and tracking anti-aircraft radar antennas, and contracted Baldwin to develop optical encoders. Baldwin produced a 16-bit device under this contract by 1953 and its first experimental optical encoder in 1955. This line of research ultimately led to the 18-bit optical encoder that became the first optical encoder used in American spaceflight in 1962. Meanwhile, the WNLE Gurley Company, makers of precision surveying instruments, was refining its own microscopic measurement techniques. Gurley had previously pioneered the use of stretched filaments of black widow spider silk to produce precision crosshairs in its surveying telescopes, but by mid-century, the toxic and labor-intensive nature of that work drove the company towards photoetching chromium directly onto glass discs. This chrome on glass process paved the way for the mass production of the digital optical encoder disc. An optical encoder fundamentally determines rotational position by shining light through a patterned disc mounted on the shaft. A focused light source sits on one side of the disc and a photodetector on the other. As the disc spins, alternating transparent and opaque regions chop the beam, creating a rapid on-off flicker that converts into a stream of digital pulses. In an incremental encoder, the disc carries a single track of evenly spaced lines, and the system counts pulses to track relative movement, typically using two detector channels offset by 90 degrees so it can sense direction as well as speed. In an absolute encoder, the disk instead carries multiple concentric tracks forming a unique coded pattern at every angle, producing a persistent, distinct digital word that correlates to an absolute angular position. Modern optical encoders achieve incredible resolutions with up to millions of counts per single revolution in high-precision variants by leveraging optical phenomena such as the Moire effect. The Moire effect is a large-scale interference pattern produced when a partially opaque ruled pattern is overlaid on another similar pattern with a slight angular or spatial offset. In a precision optical encoder, two ultra-fine gratings, with typically one moving on the glass disk and one stationary on the sensor head, are overlapped. When perfectly aligned, light passes through. When the moving disks shift by even a fraction of a micron, the lines begin to block each other. Instead of reading the microscopic lines directly, the encoder reads the Moire fringe's magnified shadow bands that shift rapidly across the sensor array. Even more advanced encoders pushes this further using two well-established diffraction phenomena, Talbot imaging and the Lau effect. Talbot imaging is a near-field diffraction phenomenon in which monochromatic light passing through a periodic grating recreates a self-image of that grating in midair at a specific mathematical distance known as the Talbot length, without any physical lenses. The Lau effect extends this principle to light sources with low spatial coherence, such as compact LEDs, allowing the encoder to operate without conventional imaging optics. By capturing these self-images through a secondary analyzer grating, the encoder translates microscopic mechanical displacement into a sweeping intensity modulation in the micrometer scale, providing both speed and directional cues. Following World War II, the aerospace industry began to face growing manufacturing challenges. The advent of the modern helicopter required rotor blades to be formed from mathematically defined aerodynamic curves. Traditional machinists shape these parts by following metal templates or tracing profiling models with hydraulic tracers that use a tracing stylus with hydraulic power amplification and a basic feedback loop to keep the cutter matched to the template. However, template-based processes were slow, depended on a physical master for every shape, and could not interpolate complex three-dimensional curves, resulting in part variation. In 1946, engineer John T. Parsons of the Parsons Corporation, working alongside his newly hired chief engineer Frank Stulin, realized that if the aerodynamic curves of a rotor blade could be defined by mathematical equations, these coordinates could be calculated and punched into IBM tabulating cards. Rather than tracing a physical template, a machine could be driven directly to each numerically specified point. Parsons demonstrated an earlier version of this idea using an IBM 602A multiplier to compute airfoil coordinates, which were then used to position a jig borer. In 1949, with funding from the United States Air Force, Parsons partnered with the Servomechanisms Laboratory at MIT to build a practical system. The lab modified a Cincinnati Hydrotel vertical milling machine, replacing the manual hand wheels with electric servo motors linked to a closed-loop positioning feedback system. By September 1952, it was demonstrated publicly as the world's first numerically controlled machine tool. The controller consisted of several refrigerator-sized cabinets containing roughly 250 vacuum tubes, 175 electromechanical relays, and a punched tape reader. It read instructions from then-standard 7-track punched paper tape that compared each desired numerical coordinate to the actual physical position of the machine bed, and subsequently sent electrical pulses to the servo motors to close the distance. Beyond basic feedback control, it also possessed a rudimentary hardware interpolator that smoothly blended the speeds of the X, Y, and Z axes using a master timing clock. This created a smooth cutting motion that tracked a continuous curve between discrete data points. While the MIT system was notoriously temperamental and expensive, it pioneered the first direct link from design to motion with precise rotational control, now a critical element in that chain. As both digital computers and automated systems rapidly evolved in the 1950s and 1960s, a new rotational requirement emerged. While the closed-loop servos of numerical control machines were effective, they were also heavy, expensive, and relatively delicate, requiring feedback sensors and tuning to function. The emerging computer peripherals industry also needed a cheap, reliable way to move mechanical parts within tape drives, early printers, and later disk drives, in a precise, repeatable manner purely by digital pulse. The solution was the stepper motor. Unlike traditional motors designed to spin continuously upon receiving power, a stepper motor rotates in discrete, fixed, angular increments, natively transforming digital pulses into mechanical geometry. The earliest iteration was the variable reluctance or VR stepper motor. First appearing in patents around 1919, it relies on the fact that magnetic flux will always seek the path of least resistance or magnetic reluctance. It's composed of a stator lined with electromagnetic coils and a rotor made of solid, laminated soft iron formed with gear-like teeth. These rotors possess no permanent magnets of its own. While the motor's controller sends a pulse of electricity to a specific pair of stator coils, the iron rotor rotates to line its teeth with the energized coils as it seeks the path of least magnetic reluctance. Because the rotor has no magnets, it has low inertia, allowing it to start, stop, and index rapidly, though it generates no holding torque when the power is removed, leaving the shaft to spin freely. In 1952, General Electric engineer Carl Fairtog filed a patent for the hybrid stepper motor, effectively combining the best traits of variable reluctance with permanent magnet technology. A hybrid stepper embeds an auxiliary magnetized permanent magnet at the core of its rotor, capped with toothed iron cups at both ends. By positioning the rotor teeth to be slightly misaligned with the stator teeth, a much finer step increment is created. A standard modern hybrid stepper typically has 50 rotor teeth per cup, yielding 200 steps per revolution or 1.8 degrees of movement per pulse, entirely under open loop command, while maintaining stiff holding torque even when stopped. This configuration proved enough for precision computer peripherals and industry control, with Sigma Instruments emerging alongside General Electric and Superior Electric as one of the key firms that commercialized the hybrid stepper. In Japan, Fujitsu's Fanuc division took a different route to open-loop motion, developing the electro-hydraulic pulse motor in 1959. This indirect method used a small stepper to pilot a hydraulic actuator for torque amplification, which became the foundation of its early CNC systems. Early stepper motors suffered from a fundamental mechanical flaw. Because the coils were energized at full current, then abruptly cut, the rotor jumped rigidly from one magnetic pole to the next, causing it to ring with each step. At certain speeds, this discrete stepping motion excited the system's natural mechanical resonance, potentially causing the motor to lose magnetic synchronization entirely, stalling or skipping steps, and losing all track of its position. The solution was the introduction of pulse width modulation paired with active current regulation in the drive electronics. By switching the drive transistors on and off thousands of times per second and measuring the resulting winding current, a chopper driver could hold that current at any target level, not just fully on or fully off. Rapidly modulating the pulse width lets the controller synthesize stepped approximations of smooth sine waves in the coils. This precise current control is the foundation of microstepping. By blending the currents in adjacent windings in fine calibrated ratios, the driver steers the magnetic field in continuous increments rather than discrete jumps, with the rotor settling into controlled equilibrium between physical poles, held by the balanced pull of neighboring coils. Modern stepper drivers can subdivide a single 1.8 degree full step into as many as 256 microsteps, transforming the stepper motor from a noisy, vibration-prone component into a smoother, far more refined open-loop device. By the early 1960s, the traditional DC motor would see a breakthrough that would open it up to more precise use. Traditionally, to keep a DC motor turning, the current in its spinning armature must be reversed continuously as each coil sweeps past the fixed magnets. Since the first practical DC motors of the 1830s, this reversal was handled by brushes consisting of spring-loaded blocks of carbon pressed against a rotating copper cylinder called the commutator, feeding current to the armature as it spun. The brushes ground themselves down into conductive carbon dust, required regular maintenance, and sparked continuously as they crossed the gaps in the commutator. The sparking capped the motor's top speed, wasted energy, and flooded the surroundings with electromagnetic interference, making them hazardous in explosive industrial settings or the vacuum of space. In 1962, driven by the emergence of solid-state transistors, researchers T.G. Wilson and P.H. Trickey would develop and demonstrate the first practical brushless DC motor, or BLDC. Originally described as a DC machine with solid-state commutation, in their approach, the copper electromagnetic coils were moved to the stationary outer shell forming the stator, while the permanent magnets were mounted on the spinning shaft, creating the rotor. With the coil now fixed in place, there was no longer any need to feed current to a moving part, eliminating the brushes and commutator altogether. However, removing the mechanical commutator meant there was no longer anything to switch the current automatically as the shaft turned. For the motor to function, an electronic controller was needed to actively determine when to energize each coil. The solution was to build Hall effect sensors into the stator. These sensors track the rotor's magnets as they pass, allowing the controller to energize the coils in sequence so that the stator's magnetic field stays just ahead of the rotor, continuously drawing it around. By the mid-1980s, the development and commercialization of rare earth neodymium magnets began to dramatically amplify the power and torque density of the brushless DC motor, creating an architectural shift in mechatronics towards the direct drive frameless motor. For a given size and cost, electric motors are generally more power dense when they run at high speeds and lower torque. To move heavy loads at useful speeds, this historically forced the use of mechanical gearboxes to reduce speed and multiply torque. Gearboxes, however, introduce backlash, mechanical compliance, and friction. The higher torque density of neodymium-based brushless DC motors now made it practical to eliminate that gear train entirely. Frameless motors eliminate the gearbox, the dedicated motor shaft, the couplings, and even the external motor housing. The stator is press-fit, bonded, or clamped directly into the frame of the mechatronic housing, while the rotor magnets are mounted to the moving joint itself, driving the load with no intermediate transmission. This creates very high torsional stiffness, smoother torque delivery, significant weight reduction, and the elimination of gear backlash since there is no gear mesh to lash. Combined with high-resolution feedback and precision bearings, direct drive systems can achieve positioning down to the submicron and nanometer scale. As industrial automation matured through the 1970s and 1980s, engineers faced a persistent trade-off between two motor types. The AC induction motor, introduced in the late 1880s by Nikola Tesla, had become the standard workhorse of industry because it was mechanically simple and durable, with no brushes to wear out and no rare earth magnets to demagnetize. However, this simplicity came at the cost of control. In applications that demanded precise dynamic performance, such as when a load must be rapidly accelerated, held at a specific torque at zero speed, or maintained at constant velocity under a fluctuating load, separately excited DC motors were the only practical choice. This is primarily because the field current and the torque-producing current are carried in physically separate windings, the stator and the rotor. This independence allowed torque to be adjusted without disturbing the magnetic field, making control straightforward and the response fast. The induction motor had no equivalent separation. Its three-phase stator currents must handle both jobs at once, with flux and torque drawing on the same current, which makes dynamic control difficult. Early drives worked around this characteristic by using scalar control that simply raised and lowered voltage and frequency in proportion. This held the motor's flux roughly constant and was adequate for steady-state operation, but it gave the drive no direct control over torque. When a sudden load hit, the drive could not command more torque instantly, causing the rotor flux to distort or collapse, leading to stalling and poor efficiency. The solution to AC motor control emerged as a form of motion control known as field-oriented control or vector control. The conceptual breakthrough was achieved in the late 1960s and early 1970s through the parallel work of Kay Hasse, who devised indirect vector control, and Felix Blaschke, a researcher at Siemens who proposed direct vector control. From this, the AC motor could be mathematically manipulated to behave exactly like a DC motor. Blaschke proposed using a real-time mathematical algorithm to shift the frame of reference from a collection of sine waves at different phases to mathematically track the spinning magnetic flux of the AC rotor. To achieve this, vector control relies on mathematical coordinate transformations developed decades earlier by Robert H. Park in 1929 and Edith Clark. Known respectively as the Park transform and the Clark transform, these techniques dramatically simplified the analysis of complex three-phase electrical systems. In modern field-oriented control drive, current sensors continuously measure the three rapid alternating sine waves entering the motor. The drive's microprocessors apply the Clark transform to collapse the complex three-phase system into a simpler two-dimensional stationary plane. Then the algorithm applies the Park transform, mathematically rotating the two-dimensional plane to match the exact angle and speed of the motor's rotor flux. While Blaschke's method directly measured the flux, Haas's indirect method calculates where the flux should be from a mathematical model of the motor and a reading of rotor position, while adding a computed slip term for the rotor flux turning slightly faster than the rotor. From this, the AC sine waves are distilled into two simple independent DC-like values, one representing the magnetic flux and the other representing pure torque. Because these values hold constant in steady-state operation, the motor controller uses a simple proportional integral loop to adjust the torque, completely independent of the magnetic field, mimicking the behavior of a DC motor. The algorithm then runs the math in reverse, applying the inverse Park and Clark transforms, converting the flat DC commands back into the three-phase wave required to manipulate the motor coils. This entire sequence is executed by the drive's microprocessors thousands of times a second, allowing AC and brushless motors to achieve unprecedented levels of dynamic performance and efficiency. The future of precision rotary control is leaning heavily into synthetic control algorithms that compensate in real time for the parameter drift, thermal expansion, and mechanical resonance that once capped accuracy. With machine learning models trained on a specific machine's vibration signatures and wear patterns, the ability to predict and cancel errors before it reaches the shaft now becomes possible. Still, the mechanical foundation will remain indispensable, though it is increasingly becoming a substrate upon which software performs the real work.